Sorry, who's against review sessions? Who's against review sessions?
This one, it's like Einstein guy in our class. He's like a little bit smaller.
I'll mute myself while I talk about things unrelated. We're gonna mute. Alrighty, do we want to get oh my gosh, the second screen. There we go. There we go. We're all good. Okay, let's get started with this. So we're going to be going through test 2 for the 2022 winter term for 2DO3. So this is the one that I wrote. I don't know how different your test is going to be because it is a different prof, but this gives a bit of an idea of the concepts that'll be covered. If at any point you have questions, or like even if it's unrelated to the exact question that we're going over, feel free to let me know. I will give the general disclaimer that once again, I haven't really prepped for this. I'm kind of just relying on the fact that phase transformations basically covers the same concepts. So yeah, so I can't guarantee that I'll know everything, but I'll be trying my best. And if I don't have an answer for you, I promise that I will look it up and get back to you after this session. Does that make sense? Okay, so we're gonna get started. So the way test 2 started is it was just a bunch of definitions. And when I took this course and Dr. Kish had been hinting at the first question literally all semester, just being like, know these definitions, know what this means. So it was pretty standard to see this, but these are really common or really like core concepts to the entire like second half of the course. So it's good to kind of go over them. So the first one we're going to talk about is the activity coefficient. Note that while I go over these, the solutions are posted in course resources as well. I don't think you needed to say everything that was in the solutions document to get full marks. Do I have a test? Yes, so we can go over what I put down so we can see what you actually needed to say to get the marks. Aha, I do have my test. Okay, give me a sec. I'm gonna get actually my test out. Alrighty. So we're gonna start with our activity coefficient. So the activity coefficient for component I in a mixture, we define it basically using the following equation. So we can say A, as a heads up, my screen is kind of broken, so I can't write in the middle of it and I keep forgetting. So if my pen goes wonky, that's why. We can say AI is equal to gamma I xi. So we can define gamma I is equal to AI over xi. And that's fine and all, but what actually is this? What does this mean? So this just kind of relates a bunch of concepts that we've talked about together. So AI is just the activity. And then xi is the molar fraction. And these are both of component I in some mixture. And basically what this kind of relates to is this shows how we have your activity coefficient gamma, so that's the coefficient. And this equation relates, there we go. This equation just relates the activity to the molar fraction together and basically describes how does this actually change. Because if you remember Raoult's law that we talked about last session, right? We have like activity, molar fraction, whatever. It's just like a nice little straight line slope of 1. It goes from 1, like 0 to 1 on both axes. And this is what all nice little mixtures do, right? If you add a certain amount of a substance, it's going to behave like that amount of that substance, right? And it's going to have that level of reactivity in the mixture. But sometimes that's not always the case. So we can have what's called either positive or negative deviation. And that's kind of what it sounds like is a deviation. So it's a change from the ideal and it'll be above or below what you would expect it to be. So we can start with negative deviation, that'd be down there. I'm gonna write negative deviation. And what that means essentially is that because it's below what we would expect it to be, then the activity coefficient is smaller than 1. So it's multiplying your molar fraction by a small amount. And what this shows is that this is like, I don't know if you actually need to say this, but just kind of to give a bit more context, is what we talked about a little bit in the last review session, is that if you have this negative deviation, right, essentially what it's saying is that it really likes, like these substances really like bonding together. So we have strong, say you have components A and B, we have strong AB bonds compared to like AA or BB bonds. And what's that saying is basically they really like existing together. They really like just existing as a mixture and they don't want to be reactive as their individual components. They don't want to, yeah, that's kind of what it indicates. We also know that it's going to be exothermic, so delta H is going to be less than 0. And the way I like to think about that is it's negative deviation. Our, enthalpy is going to be negative because it's exothermic. We also have what's called positive deviation, where we go kind of the opposite. So we skirt above, and that's going to be the opposite of what I just talked about. So this is where gamma I, the activity coefficient, is greater than 1. We're multiplying the molar fraction by some value so that it's bigger than we would expect. And what this means is that as we mix it together, then it really doesn't want to mix. It's really not a fan of being in that mixture. It doesn't want to exist with the other component. So that's why it's a bit more active than you would expect. So we can describe that as having weak AB bonds. At least that's how I like to think about it. And then this is going to be delta H is bigger than 0, so it's endothermic. And that's kind of the gist of this. That's kind of the gist of what the activity coefficient is what it comes down to, is it's just this little gamma value there, and we use it to describe a few different things. Are there any questions so far? Taking that as a no. As a reminder, these notes will be posted afterwards, so if I move on too fast, let me know and I can go back, but you'll also have access to these. Okay, the second thing I wanted us to talk about is the Gibbs-Duhem equation. So the Gibbs-Duhem equation is essentially, wow, I really went extra for this test. The Gibbs-Duhem equation is the sum of qi xi is equal to 0, or at least that's what I wrote. Let's see what the solution actually said. Yeah, so that's what I wrote down. You can also describe it in terms of the moles and the Gibbs free energy, right? Either of these are appropriate. Essentially what we're saying, whoa, where are you going? Yeah, if you can go there, that'd be nice. Essentially what we're saying is if you add up, a given amount, so like we can say that amount is either xi or ni, like whether it's the molar fraction or the moles itself, and then we add up the energy of mixing that, right? Whether that's the Gibbs free energy or whether that's just like Q as in any extensive property. This is a more generalized view of putting it, because Q can be G, H, etc. But you can just think of it in terms of Gibbs free energy. But if you add up all those little bits of how that's going to change the Gibbs free energy for a given molar fraction, it's going to be equal to 0. And that's a little bit hard to kind of understand. Did I really need to put that? Give me a sec. Let me just see what you're actually being graded on. Yeah, so I went into, I think I didn't, when I was writing this, I remember I was like a little lost as to what to say to get all the marks. So I started talking about like what we had done on the assignment and how you use that to calculate the activity coefficient. You didn't need to put that down. So I'm going to ignore that for now. But if you're curious about that fun little mathy math, I can go over it afterwards. But really all we're saying here is that this is for a system in equilibrium, right? And we're not going, like, if this equation must be true for a system at equilibrium. Because if we're at equilibrium, we're not going to, like, you think of like a, Gibbs free energy graph, you have like delta G, X. If we're at the bottom, right, that change in Gibbs free energy, we have a horizontal line when we're at our local minimum. So that's going to be a slope, like that change in Gibbs free energy, delta G, is equal to 0. If you think about the slope, if that kind of makes sense. So that's the Gibbs-Duhem equation. Are there any questions about that? Go for it. Yeah, that graph part is just me kind of spitballing words. The way I can think about it, let me just see exactly what they say here. Such wordy words in the solution. The way that I think about this, this isn't technical in the slightest, okay? This is not like the formal definition. This is just another way to look at it, is that we're at equilibrium, right? So if we think of equilibrium, we think of a Gibbs energy, here instead of calling it delta G, we think of a Gibbs energy versus molar fraction graph. At that bottom, at that local minima, we're going to have like the dg dx is equal to 0. Like just the slope of the graph is equal to 0. So the way I kind of look at that, again, this is not mathy in the slightest, is I'm like, well, that change in Gibbs free energy, right? If we add up all of the different little bits and pieces in the mixture, and that total, if we sum them all up and we add like the total dg for changing these bits, is going to be equal to 0. Because we're at equilibrium. So it has to be equal to 0. Again, that's not actually technically correct, but it's another way of kind of thinking about, we know that it needs to be equal to 0. Here's a way that we can think of Gibbs free energy being 0. Does that make a bit more sense? That's how I'm thinking of it right now, yeah. Again, is that like the actual way of approaching this? Not really, but it's a way to think of it. Another thing that you can, sorry, I'm just going to say this and then we can go into that. Another thing that you can think about with the Gibbs-Duhem equation is we can use this to calculate, to calculate the activity coefficient of a component. Yeah, so that's just another thing that we can use the Gibbs-Duhem equation for. I don't know if you actually needed to say that to get the marks, but yeah, that's another thing it's used for. You had a question. Yes, I can post that as well. It's also in course resources already, but for ease of access, I'll put it in there as well. Alrighty, I'm gonna move on. Part 3, regular solution. So when we're talking about a regular solution, we got to first go back to what the definition is of an ideal solution. So we can think in an ideal solution, we're mixing two things and they mix together and they're all happy, right? We think of like, and we're imagining that graph, AI and XI, they're all happy. They're interacting, like they're behaving just as you think they would. Nice straight line. There's no real actual interactions going on there. All we're doing is we're mixing them together and they're just as happy to be bonded like A and B or by themselves like AA. So like it's totally fine wherever. And if we turn that into like actual, thermodynamics terms, we can say that the delta H of mixing is equal to 0. So again, what this is saying is that, we're going to have delta S of mixing is not equal to 0. We're going to be changing our entropy because we're adding disorder to the system as we mix A and B together. You know, it goes from being A and B to being all over the place. So that's going to add disorder to the system, but they're not going to be forming any sort of preferential bonds. They're not going to be trying to clump together, trying to space out. They just go wherever the mixing goes. So our delta H is going to be 0. On the other hand, we have a regular solution, and that's basically just the opposite. So in this case, delta H of mixing is not equal to 0. So now delta H of mixing isn't equal to 0, and delta S of mixing is not equal to 0. So kind of what this is showing is that, essentially what this is showing is that as we mix together, so we have like a bunch of A molecules here, and then we have a bunch of B molecules over here. And now we start mixing them together. And depending on how the system behaves, it's not going to mix together nice and willy-nilly however it wants. It's going to be like, maybe like the A stuff really likes each other. So it's going to clump up together in A, you know, and then like the B is going to surround it maybe. Something like this, for example. And we're going to be forming these like bonds. We're going to be releasing energy or absorbing energy as we do this. And that causes delta H to not be equal to 0. Another feature of a regular solution is basically, we're going to get into this in like 2 more questions, but we can characterize this bonding, we can characterize this behavior using a parameter that we can call omega. It's, oh gosh, it is actually called the interaction parameter. My touch screen is actually terrible, so it's glitching out on me. Oh, everyone's going to see my passcode, aren't they? No, you're not. Okay, we're back. Are we? Yeah, there we are. Yes, please select this. Actually hit my laptop. Give me a sec. Whoa. Whoa. So we can define the interaction parameter as omega. And essentially, this is defined using some funky dunky equations that we're going to get into again in like 2 questions. But what we can say is that delta H of mixing is going to be equal to this parameter times XA, XB. So if we take this, now we can say that delta G of mixing, you know, G is equal to H minus TS. You know, just very classic. So now if we're doing mixing, that's going to be delta H of mixing minus T delta S of mixing, which is equal to omega XA XB minus T delta S of mixing. So we can use this kind of to define our regular solution. Note that this is a very specific case of a non-ideal solution. A non-ideal solution refers to anything whereby this equation doesn't hold. And our definition of this interaction parameter omega is just a specific case of that non-ideal solution. It isn't every kind, like it isn't one or the other, but that's kind of how we treat it in this course. Does that make sense? Go for it. Yeah, I think, yeah. When you get into phase transformations, then you start talking about a few like other kinds of what can happen, but in this course, you can just think of it as ideal or regular. Alrighty, moving on, excess thermodynamic value. Basically, what this represents is it's anything that is non-ideal component. And it's just the way that we term this non-ideal component of our of any sort of solution. So for example, if we have a way that we can define it, you know, we're going to go back to another definition for Gibbs free energy. So we can go to like the Gibbs free energy of a singular component, right? Gibbs energy of I. We define this as RT ln the activity of I. This is just like one of the standard definitions for Gibbs free energy. And if we're dealing with something that's ideal, remember, ideal, then Xi is equal to Ai, right? It's equal to the molar fraction. So then we just have Gi is equal to RT ln Xi. But that's not always the case. So we can define it using our more generalized solution with, you know, Henry's law and all that jazz, is now we can define GI is equal to RT ln. In this case, we have gamma I, whoa, xi, because we remember AI is equal to gamma I xi. And if you were to split up this ln term using ln rules, you get RT ln xi plus RT ln gamma I. So what we see here is that our first term, this is the exact same as G ideal, right? That's the exact same. So that's like just chilling. It's right there. But then when we have a non-ideal situation, we're adding on this little bit at the end or subtracting it, depending on what the value is of gamma I. But the point is we're adding this value, we're adding this term. So that's going to be non-ideal. And that represents, this is the excess value. Another way you can think about it is that, or another way that you can kind of approach an excess value is that in an ideal solution, the delta H of mixing is equal to 0, right? But when we have a regular solution, or just like, yeah, we'll do a regular solution, our delta H of mixing is equal to, you know, omega xa xb, which is not equal to 0. So we're adding this to our already, you know, to our Gibbs free energy and to our enthalpy term. So this is all going to be delta H excess. If we talk about a regular solution in general, again, this is probably getting a little bit too in depth for what the question is actually asking, but just for the sake of all being on the same page, we talk about a regular solution in general. Remember, G is equal to H minus T delta S. And we already agreed that T delta S of mixing ideal is going to be equal to delta S of mixing non-ideal. Because no matter the way you mix it, like it's all going to get jumbled up. So delta S is just kind of like, yeah, we add a little bit of A, a little bit of B. There's the same number of possible configurations. It's the same delta S of mixing. So that means that delta S of like excess is going to be equal to 0. So if we're trying to find the Gibbs free energy that's excess, G excess is going to be delta H excess plus delta S excess. We already decided that delta S excess is going to be equal to 0. So we can say that delta G excess is going to be equal to delta H excess, which is equal to omega xa xb. So again, that's a little bit like extra for what this question was asking, but in case that question comes up, I think it's good to cover, just talk about how a regular solution has various types of excess energy within. Go for it. Yes. Because this is the delta H of mixing for a regular solution. And this is all equal to delta H excess because delta H excess is equal to delta H non-ideal minus delta H ideal, which is equal to omega xa xb minus 0. Does that make sense? Go for it.
Let me make, I guess, my extension. Or delta S access, then the delta G access is like not.
Correct. Alrighty, I see no more hands. We're going to move on. Remember how, like, I don't know, 5 minutes ago, I have no concept of time. Then I was like, we're going to get back to the interaction parameter. Ha, we're back to the interaction parameter. So the last part of this question was define the interaction parameter for a regular solution. So we're going to scoot down there. So the interaction parameter, depending on your definition, can be defined as parameter, can be defined as either omega, oh, we're in the middle of the screen, omega or alpha prime. I'm going to use omega because I kind of like that better, but depending on your teaching, it might be different. So this is defined for a given solution. So it's constant for a regular solution. And it is independent of temperature. because this essentially, this acts on the enthalpy of the solution, right? This talks about the bonds present. The bonding that's happening isn't going to depend on the temperature. Like those bonds are going to form no matter what. The temperature only really affects the entropy. So the way we define this, essentially, I'm just going to write the equation and then I'll explain it. Z times N naught times EAB minus 1/2 EAA plus EBB. So this is the definition in equation form, which I believe you were required to write out for this question to get the marks because it asks for mathematical definitions. And this has a few key concepts in it. So this in here is talking about the change in energy when a bond is formed. So we start, you can imagine we start with like A, 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 A. You know, we have like a bunch of bonding, and then we have like B, 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 whatever. So each of these little E values is equal to a bond energy. So we start and we have all these BB bonds, you know, and we have all these AA bonds, and now we form a bond in between. So essentially what it's saying is instead of having an AA and a BB bond, now we have something AB. So that's what this is saying, is this is like, what is that change in energy as we do that? And notice that we have this little 1/2 here. The reason we describe that is because we add one AB bond for every, like, we have one BB bond and one AA bond that are broken. So that's 2 bonds total, but we're only forming one new bond. So we have to multiply it by 1/2. Does that term make sense? Go for it. Yes. All of it, or just the part about the 1/2? Yeah, so we can think of it as, I'll draw my drawing a little better. We have, you know, we have this lattice of B bonds and we have this lattice of A bonds, you know, they're all happy. And then essentially we need to break one B bond, we need to break one A bond in order to form that AB bond. So we form one bond. That's going to be EAB. But then we break 2 bonds. Another way you can think about it, instead of like breaking the bonds, is that we form a bond between A and B. Form a bond between A and B, and then we break a bond between AA and a bond between BB, but each of those bonds is being shared by 2 molecules. That, I don't know if that makes any more sense. But you can think of it in terms of also like we break 2 bonds, EAA, EBB, but we only we want to keep the number of bonds consistent because these other molecules, you know, like this A molecule that we broke the bond and this B molecule, those are going to go off and do like their own bonding. You know, like they're going to bond to another A molecule and they're going to get their EAB of their own. So we need to like just put it in terms of each bond form and each bond break. So that's why we have to divide by 2. Does that make sense? Okay, go for it.
Okay, so that actually made sense to me. It's because like if you had an infinite system of A,
Yeah.
wouldn't they all break and then reform to create like that 1-to-1 ratio? It's like
Exactly. That's why we need to divide it by 2, because we're going to end up with a 1-to-1 ratio. Like if we have, if we start with, because you're right, we're like thinking of like infinite systems. So if we start with like A bond, let's just make it a really simple system. We have A bonded to A and we have B bonded to B. If we just look, and then we're gonna, you know, break these bonds and we're gonna form AB, right? We form one bond here. But to do this, we're imagining these things can only bond one thing at a time. We need to break this bond and this bond. So we need to divide that by 2. And the reason this kind of makes sense is that we can also form a bond in here. So another way you can think of it is as we take half of this bond for this side and half of this bond for the other side. Yes. That is another way to find it. So yes, you're right. So we have the equation alpha is equal to omega over RT. Do you remember what alpha is? I remember it actually didn't have any meaning. It was just like a parameter that you could use to find other things. Yes. Yeah. So the key here is that even though we have temperature in the equation, omega is still going to be constant and independent of temperature. And what's going to change with temperature is our alpha value. Does that make sense? Amazing. The last few things to go through with this equation is basically just, we also have these two terms here. We have Z and N naught. And essentially this represents the number of bonds that we can make. So like when we're talking about the simple situation of delta E, remember, like I could simplify it to just being A bonded to B, A bonded to A, whatever, right? But in reality, if we're talking of like an FCC crystal or something, right, you're going to have a molecule bonded above, in front, to the side, you know, all sorts of things. So we have this coordination number Z. And then we have like, you know, a bunch of lattice sites and not. So basically, omega takes into account not just one atom, but all of the potential atoms, all the potential bonds in the system. Does that make sense? Yes. Z was the coordination number, and then N naught is the number of lattice sites. Maybe that's it. What does it say in the solutions? Oh, it 100% is Avogadro's number. I don't know why they gave me full marks for that. Avogadro's. Play. Alrighty. Are we good to move on? Go for it. This?
Yeah.
This is another way of defining omega using the value alpha. So this kind of goes down to another way that we can define omega. Essentially, we can define, you know, an equation, ln gamma A is equal to alpha x b squared. This is like, I don't remember the full derivation to get this, but this is another equation that you can use to relate our activity coefficient to our molar fraction, right? There's a bunch of funky math derivations. I don't really remember, but there's this equation. And using this, we can solve for this value called alpha. And alpha is the way that it describes the bonds going on in the system. However, this alpha does depend on temperature. So this depends on temperature. And us as engineers, we like nice constant values. We don't want to deal with things that are changing all the time. So this is why we then took this equation and we, you know, can also rewrite it as omega is equal to alpha times RT. So we redefined a new parameter called omega that is now independent of temperature. We get rid of that temperature dependence in order to make our lives a little bit easier. Does that make sense? You too. Alrighty, we're gonna move on to the next question then. Well. You're not be your touch screen for one bit. You can do it, Wanda. You can roll. I believe in you. Okay, I'm going to take 1 second and close window and then open it again. Gonna stop sharing my screen, close this, close that. Okay. Oh, and now you're working just fine. Actively? Screw you. Share my screen. Apologies for that. My OneNote hates me sometimes. Alrighty, are we good to keep going? Sorry for that delay. My computer is a little wonky sometimes. Okay, so now we're given a little bit of experimental data and it's like, ooh, what's going on here? Essentially it gives us some data. It's like, ooh, this is what the data is. It's electrochemical and it's measured at this temperature. For now, all I really care about is the data itself, and I see X and I see gamma. So that is something that we can look at. The first thing is like, is it regular solution behavior? And if we go to regular solution behavior, we can define, remember, a few things. We can use a few different ways to define what regular solution behavior is. So we can say for regular solution, delta H of mixing, remember, is not equal to 0. Our delta H of mixing is going to be equal to omega XA XB. We also know that the delta S of mixing is going to be equal to the delta S of mixing ideal, which is equal to R ln Xi ln Xi. That's just the definition for what the, that's the definition for the entropy of mixing. We also know that our omega value is going to be a constant value, and we know that it's going to be equal to, I guess, it's going to be constant. We can define this omega value. Remember, ln YA, or ln gamma is going to be alpha XB squared. So this is the equation that I talked about earlier. The derivation for this equation I could not go into. I don't remember it. But we can remember this equation, and we can use that to derive our quantities that we actually are going to use. So we remember that alpha is equal to omega divided by RT. So we're going to sub that in, and we can say ln gamma A is equal to omega over RT XB squared. So if we were to solve for omega, now we get omega is equal to RT ln gamma A all over XB squared. So essentially what we can do here is that we can look at the system and you can say, okay, we have a temperature, we have X, we have gamma. If we know that it's going to be a regular solution, we have all the values we need, R, or I guess R is not a value we need. We have T, we have gamma, we have X. We can use that to calculate our omega value. And if that omega value is constant, we can say that it's going to be a regular solution. So we can go through and do just that. So I'm going to make a little table. I'm going to say we have X of C, and then we have gamma C. So this is the value that's given. These are given. Then we also are going to have the activity of C, and then X of Z. The reason we know it's Z is because it's a ZnCd liquid mixture. So we know that there's just zinc and I think it's cadmium that are going to be present in this solution. So I'm going to just call them Z and C. And now I'm just going to kind of throw these in a table and calculate them. Oh boy. One of my friends in this test, I think, made like a calculation error in this first step, and it was like the most tragic thing. 0.2, 0.3, 0.4, 0.5, 2.153, 1.817, 1.544, 1.352. So the first thing I'm going to calculate is I'm going to calculate the activity of C, right? And the way I'm going to do this, so that's going to be that row in there, is we're going to remember that the activity of I is equal to gamma I times X of I. So I'm just going to take, for example, for this value right there, I'm going to say the activity of C is going to be equal to gamma C times XC, which is equal to 2.153 times 0.2. If you were to calculate that, you get a value of 0.4306. And theoretically, you can do that for the rest of the values. I'm going to fill them in the nature of time. 0.5451, 0.6176, 0.676. We're not going to be using that directly right now, but we might use that in future values at least. Yeah. The next thing I'm going to calculate is our x of z. So this is the molar fraction. We know that there's only two components in the mixture. So you know that 1 is equal to xc plus xz. So to calculate xz, I'm just going to do 1 minus xc. So for example, this value right here, xz is going to be 1 minus 0.5, which is equal to 0.5. I'm going to fill those in. So now I have this value. I took all the experimental data and I kind of fiddled around with it a little bit. And I'm going to go through and I'm going to calculate that omega value for each of these instances. I'm going to add another row here, omega. And I'm going to use this equation here. The key here to remember is that our temperature is equal to 527 degrees Celsius. We don't care about temperature in Celsius. We need to convert this into Kelvin. So that's going to be 800 Kelvin plus 273. And then we know that R is equal to 8.314 something units. I forget the units, but you know, it'll all work out. And now what we're going to do is we can just sub in these values. So for example, for the first value, we're going to say omega is equal to 8.314 times 800 Kelvin times ln gamma A is going to be 2.153. And we're going to divide that by xb squared, which in this case is xz. That's going to be 0.8 squared. If you were to calculate that, you would get a value of 7970. So you do that for all of the values, 8106, 8025, 8024. And we look at these and we're like, okay, I know that for a regular solution, these are all going to be constant because it's independent of temperature. It's independent of, if you remember the definition for a regular solution parameter, right? We go up here. The only thing it depends on is the bond energies, which isn't going to be changing if we're adding different amounts of each. We're changing the temperature. And we look at this data and it's not like exactly the same, but they're all pretty close. So what we can say is that they're calculated experimentally, so they're not going to be exact. And these are close enough that we can say it is a regular solution. Does that make sense? I am going to see if that's exactly what the solutions put. I won't lie. Yeah, okay. All right, so now we go up and part 2 is asking us to calculate the values of the partial molar heat of mixing, the integral heat of mixing, the integral molar entropy of mixing, the partial molar free energy of mixing, and the integral molar free energy of mixing for an equiatomic mixture, assuming regular solution behavior. So that is a lot of words. Let's break it down a little bit, shall we? So, it says equiatomic. Fun fact, when I was taking this test, I did not read that word, and I was like sitting there for the longest time being like, how the heck do I do this? Yeah, it's equiatomic. So we're gonna look at this and we're just gonna start by writing down everything that we know about the situation. So we know it's equiatomic. That means that they're equal molar fractions. So Xc is equal to 0.5, Xz is equal to 0.5. Nice thing we know. Next thing we know is that we know the temperature is equal to 800 Kelvin. Again, that was given to us at the start. Now we can go back to a little bit of our now we can go back to a little bit of the information that we calculated in the previous step. So we know, or that we're given or we're calculated, we know that gamma C is equal to 1.352. We know that omega is equal to, we can take the average of all of these values, average, and I'm just going to sit there and say that's 0, or not 0, is it 8031? I'm also just going to write down the activities. So we know AC is going to be equal to 0.676. Again, we calculated that for the table above. But now we look at this and we're like, where do I get these values for, Z for the zincs. Go for it. Great question. It says equiatomic mixture. So equiatomic means equal molar fractions. Of course. Sorry if you had your hand raised for a while and I completely missed it. There's so many words going on in this question. I'm a little
No, I don't.
dialed in. Okay, so now we look at this and we're like, well, we're probably going to need to know the activity and the activity coefficient for zinc. We don't just need that for the cadmium. So how do we calculate that? And the way we do that is using, remember, the definition of ln gamma z is equal to alpha times x c squared. So I believe we defined this earlier up. Yeah, it's just this equation, but I put in alpha. So I'm actually gonna sub that right here, omega over RT. So we know what XC is. We know it's gonna be 0.5. We know the temperature. We calculated omega in the first step. We can use this to calculate our activity coefficient. So if we were to solve for this, we can say our activity coefficient is going to be equal to the exponent omega over RT XC squared. And then we can just sub in our values. So that's going to be 8031 over 8.314 times 800 times 0.5 squared. If you were to calculate all that, you will get a value of 1.352. From there, we know that the activity is going to be equal to the activity coefficient times the molar fraction. Whoa, which is 1.352 times 0.5, and you get a value of 0.676. So it actually matches the cadmium, but it's good to do that calculation, if only just to refresh ourselves, refresh our memory of what these equations are. This little equation there, that little equation there. So we go back to the question. We're like, okay, we kind of wrote down, not word vomited, but like we number vomited onto the page. We wrote down a lot of the things that we know. Now let's start thinking about what it's actually trying to get us to calculate. So the first thing that I'm gonna look at is I'm going to look at the system as a whole. I'm not going to look at any of these individual components. So I'm just going to try and calculate delta H of mixing for the system. And the reason I'm doing this is because I already know all the values for this. I don't need to think too hard. Delta H of mixing for the system is just equal to omega XA XB, because it told us, even if we hadn't done part A correctly, it told us to assume regular solution behavior. And this is just the definition of what makes a regular solution, is that it has as interaction parameter omega such that this is true. So we're going to go through and we're going to calculate that. We're going to take our value that we calculated, say 0.31, I think it was. Yeah, and then we know XA and XB are both equal to 0.5. We throw that in our calculator, we get delta H of mixing is equal to 2008 joule per mole. Units are important. So our omega parameter is going to be given in joules per mole. Neither of these have units. So we end up with joules per mole as our final answer. The next thing that we're going to look at, again, I'm going to just stick with looking at the entire system right now, because for me, that's a lot easier than breaking it down by parts. So we're going to look at delta S of mixing. And what we can remember here is that even though this is a regular solution, remember, when we're mixing things together, it's not mixing together any differently than it was before. When we're mixing things, we don't care about what the bond energy is. We just care about, oh, well, are there a lot of different combinations possible? Is there disorder here? So we're going to say that this is equal to delta S mixing ideal. And that's going to be equal to our nice little definition of negative R sum of xi ln xi. And if we were to calculate this, we would just say negative 8.314. I guess I'm going to add in units here, joules per mole K. Oh, hopefully my laptop doesn't die. And then remember xi, so like xc is equal to 0.5, which is equal to xz. They're both 0.5. So this is actually nice and convenient. We're going to have 0.5 ln 0.5 plus 0.5 ln 0.5. If you were to calculate all this, you would get a value of 5.76 joule per mole Kelvin. as your final delta S of mixing. Alrighty. So the last thing I'm going to do with this general system is calculate our delta G. I'm actually going to do it in the same line. I feel like that makes most sense. We're going to do our delta G of mixing. And the way we do this is just, fascinating. So there's two different ways we can look at doing this. I think. I don't know why I did this way and not the other way. So I'm going to start by doing what I did in my test, and then I'm going to calculate the other way to make sure it still makes sense. Is we can define the delta G of mixing is equal to RT, then the sum of XI ln activity of I. So keep in mind that this is very similar to the one for our entropy, but in this case, we have to add a temperature. And then we also, whoa, it's glitching out on me again. Thank you. Okay, can you not do that, please and thank you. Sorry, OneNote actually, I don't know if it's OneNote or if it's my computer, but it actually just glitches so bad sometimes. Close that real quick. Are you gonna close? Are you gonna crash? Nobody knows. I told you to close. Can you? I'm so sorry. Anyways, I'm gonna say words while we're waiting. Let me actually just test something real quick. Why did I do it that way? Okay, so we will be on standby while my computer dies. I love technology. Okay, here we go. It is still recording. Now I'm going to share my screen. Okie dokie. Anyways, so this is one definition. This is very similar to our calculation for entropy, but remember, in this case, we're not just talking about the ideal component of mixing because we're using our activity, not just the molar fraction there. So if we were to calculate this, you can plug in the values 8.314 joules per mole times 800 Kelvin times, that's going to be 0.5 ln. Remember, we calculated our activities back when we were starting this question. We have them right here, so we can use that. It's going to be, 0.676 plus 0.5 ln 0.676. You were to throw that all in your calculator, you would get a value of about negative 2600 joules per mole. But let's say you kind of forget that equation exists. Maybe you're sitting there on a test and you're like, man, I remember there was this nice funky donkey equation, but I don't really remember. Luckily for you, there's the exact same equation we've always been using. Why didn't I use it in this case? Could not tell you. But it gives you the exact same answer, and that is just simply G is equal to H minus TS. No matter whether you're dealing with a regular solution, an ideal solution, mixing, delta G, like any sort of system where you're talking about the Gibbs free energy, this equation is going to be valid. So we can take our delta G of mixing minus our delta A, we can use this using the values we just calculated. One downside of using this, maybe this is why I didn't use it, is because if you got something wrong in the past steps, you won't get the right answer here. They should hopefully still give you the marks if you have the right process, but I think I might have been a little sussed out, and that's why I didn't do it. But basically, we're going to take our values that we solve for, so that's going to be 2008 minus 800 Kelvin times 5.76 joule per mole K, and you're going to end up with the value, I'm going to circle that, of basically the exact same, negative 2600 joules per mole. So either one of those methods is completely valid and will get you the right answer. Go for it. Like RT, and then it was like X ln X plus
Yeah.
X. That is the delta G of mixing for an ideal solution. Remember, we need to generalize it a bit when we're talking about non-ideal solutions. So instead of putting our second X being X, we need to convert that into our activity. And our activity is equal to, remember, activity coefficient times X. So that's why we use this equation instead. Does that make sense?
Yeah.
Yeah. And you can use this one, like with the activity, for ideal solutions as well. Because if we have activity is equal to gamma times X, for an ideal solution, gamma is equal to 1. So it's going to end up being X ln X plus X ln X anyways. Go for it.
Why don't we then write A over? Why do we drop the gamma term? Like, I don't know.
Here?
Yeah, like, can we do activity, right? But like, I don't know, I always think delta G RT, it's like one activity is like, it's like.
If you didn't want to calculate, we calculated activity at the start because I just wanted to get it done out of the way. Another way you could have written this would be equal to, it's equal to RT, and then it'd be like XI ln, instead of the activity of I, we could have said like activity of I is equal to, you know, gamma times X. We could ln gamma X plus X, I guess, J ln gamma X. Is that kind of what you were asking?
Yes, but then why don't I then think X is in the brackets, then why would I do a?
Oh, like for this term right here?
No, I mean like in the long term, right, it's
Yeah.
it's A.
Yeah.
Right?
Yeah.
But isn't it, when we relate A back to mole fraction, isn't it A gamma equal X? Or is it A over gamma equal X? Why don't we do A over gamma?
Because you're thinking of it in terms of the backwards root of what it actually is. So you're thinking, we want to turn, okay, the way at least I see that you're thinking of this is that you're thinking of it as in like in terms of like RT and then the sum of XI ln XI. And we want to turn that into XI ln AI. And if that was the case, we want to sub that in, then yes, XI is equal to AI divided by gamma I, right?
Yeah.
But in reality, we're looking at it in the backwards sense. We're looking at it in the other direction. Instead of thinking about turning XI into AI, the AI is the more generalized case. This is the one that we want to think about. So instead of going XI is equal to AI times gamma I, we can think the other way where AI is equal to gamma I XI.
So it's, okay, so the X, so that, okay, so that like the top one, that's the ideal case.
Yeah.
It's the more general.
Yeah,
way of-
using the activity is more general.
Okay.
Before.
It's the.
Yeah.
And like G is RT ln XI plus RT ln gamma.
Yeah.
I. Could you not use that?
You could use that. That is the exact same thing as just subbing in the activity. Because the activity is equal to gamma X. I just smushed them all into the activity because I calculated that previously. But you're very right. You could just write this as G is equal to RT ln XI plus RT ln gamma I, where this represents the ideal and this is the excess. Sorry, say that again.
The gamma.
Yeah, yeah. Well, in this case, we're really just breaking it up, right? Like this is equal to RT ln gamma I XI. Go for it. Like up here?
Yeah.
This is a side tangent. You don't have to do that for the question. Yeah, all good. That was a side thing. Realistically, all like this is a lot of like kerfuffle. All you really use whatever makes sense to you. These are all correct in their own way. I like to think of it as just RT the sum of XI ln AI. That is the way I like to think of it, as just like the base case, and then if it happens to be ideal, great. That's the same thing as using the x's. But that is the most generalized formula for the situation. Does that make sense? Beauty. I'm gonna give it like 2 more seconds before I move on. Amazing. Okay. So we did all the fun stuff of calculating, you know, GHS for the system. Now we have to go and we have to calculate these individual molar quantities. So the way we can, okay, let's look exactly what it asks us to calculate so I don't completely trip up. Basically, it wants us to calculate delta H as well as delta G for each of the individual components, right? We can't do delta S for this because delta S relies on mixing them together, right? It relies on like the incoherence of the system, or like the disorder of the system. So that kind of computes both of them at the same time. But delta H, you know, that has to do with the bonding present, and delta G that has to do with just the overall energy. We can do those for the individual components. The way we're going to do this is you can look at that and you be like, wow, I really have no idea what I'm doing, but it's not really that bad. If you remember, we were calculating delta G of mixing, right? We said this was equal to RT and then the sum of Xi ln AI. What if we just take this and we're like, let's break this up. Well, let's break this sum up into being component C and component Z. So we can say it's going to be equal to RT times XC ln AC plus RT ln RT XZ ln AZ. Essentially what this is saying is this is G for C, and this is going to be G for Z. This, however, has to do with the whole system, right? This is like, wow, we have like a total, like we're mixing these things together. If we're talking about just an individual case where we're like, what was the exactly called? It was the, it's like the partial molar free energy, right? What we can do is we can basically drop the x's. We can drop those molar fractions, because now instead of being like, well, we're only going to take 0.6 of that because it's only like 0.6 of the solution, I guess in this case it'd be 0.5. We can just drop that and we can say that delta G of mixing of C is going to be equal to RT ln activity of C, and delta G of mixing of Z is going to be equal to RT ln activity of Z. So we have all of these values, right? We have T was given to us 800 Kelvin. Remember, we calculated the activities a while ago where A is equal to 0.676. So if you were to sub in these values, it would be 8.314 joules per mole times sorry, I'm tripping a little bit on the units. I would just ignore the units here. 0.314 times 800 times ln 0.676. It's going to be the exact same equation for that. And you're going to end up with negative 2,604 joules per mole. That's going to be negative 2,604 joules per mole. We can do the kind of the same concept with our enthalpy. So delta H of mixing, we can say that's equal to, there's a couple different ways that we can approach this. So the first thing is to think of it as being like, it's a regular solution. Another thing that we haven't really talked about is like the graphs of regular solutions. But theoretically, if we're talking about delta H, oh, that is not an H, delta H over some sort of like molar fraction X, for a regular solution, it's going to be symmetrical. It's going to be a little, that was like the worst symmetrical drawing I've ever done, but you know, vibes. So if we look smack dab at the middle here, we can see it's symmetrical. We're going to have a horizontal tangent. Again, doesn't really look horizontal, but theoretically that's the case. So these intercepts are going to represent the molar enthalpy of mixing for each of the cases. And it's going to be the same for both. So if looking at this, we can see their intercepts are going to be the same. And we can say that delta H MC is going to be equal to delta H M Z. And we can see that's because it's a horizontal tangent, that's just going to be equal to delta H of mixing in general. It's just the value that we got, which is equal to 2008 joules per mole. And that's just kind of defined because it's a symmetrical solution. Another way that we can look at it is that delta H of mixing overall is equal to X C delta H of mixing C plus X Z delta H of mixing Z. So we can take this and we can say that XC is equal to XZ is equal to 0.5. So now we have it's equal to 0.5 delta H of mixing C plus 0.5 delta H of mixing Z. And now we can say that, well, we know that they're going to be the same because we know it's a regular solution and it's going to be symmetrical. So now we can say that delta H of mixing C is equal to delta H of mixing Z. And we're just going to call that in this case H. So then we can have 0.5 H plus 0.5 H, which is just going to be equal to H. So that's going to be equal to the delta H of mixing. So that's another way of like kind of putting some more math to what I was just saying before. But it's really just, again, coming down to that definition of in a regular solution. Remember, all delta H is equal to, you can also like think of it this way, delta H of mixing is equal to omega XA XB, which if you were to, expand this a little bit, that's omega XA 1 minus XA, which is going to be some sort of, I'll call it A times XA squared plus B times XA plus C. It's going to be some sort of quadratic like that. And you can, math it out to say that it's going to be centered around 0.5. Again, this is like completely, you don't need to know any of this. But if you're more of a numbers person and you're like, Sarah, I actively despise graphs with every being of my soul, I'm sorry to say that you're in this course. You have to know graphs. But that's another way of kind of approaching a system. And that was the end to question 2. So I'm going to take a bit of a breather. Are there any questions? Go for it. It's like, which came first, chicken or the egg, at least from my perspective, is that like, how do you define a regular solution? Do you define a regular solution based off the enthalpy, or is the enthalpy based off the fact that it's a regular solution, right? But the truth is that for a regular solution, this is true. Does that make sense? The reason I drew the graph was kind of to, I guess, graphically demonstrate how we're at 0.5, so we're going to have the same, it's going to be a horizontal tangent, so all these values are going to be the exact same. More of a pictures way of looking at it. I can look and see what this solution is technically said.
Well, this is
Yeah. Okay, so there's another way of looking at this. If, again, you're more of a mathy person and you're like, Sarah, that graph actually makes me want to cry. I don't want to deal with molar free entropy of mixing and all that jazz. There's another way you can look at this, and this is the way the solutions did it. So this is going to be a bit of a side tangent of what I covered, but something to consider. So remember back when we defined excess thermodynamic values, and we were like, okay, so delta G ideal is, we know that G is equal to H minus TS. Right? We know that delta G ideal, we can define it a few different ways. We can say that that's equal to RT, the sum of Xi ln Xi. We can say that it's equal to just, negative T delta S ideal. Whatever floats your boat. And now we take delta G of non-ideal. And this is equal to RT, the sum of Xi ln activity of I, which is equal to delta H non-ideal minus T delta S ideal. So what we can think about here is that this entropy term, this is the ideal component. So that means that all of the non-idealness of our system is coming from delta H. So anything that's non-ideal in a system is correlated to the enthalpy of mixing. So we can go back to this definition here. I'm going to expand this out a little bit. So we know that delta G is equal to RT sum of xi ln AI. I'm going to expand this out knowing that AI is equal to xi gamma I. So I can say that's RT, the sum of xi ln xi gamma I. But then I know that if I have ln of A times B, that's equal to the ln of A plus the ln of B. So now I can say that this is equal to RT, the sum of xi ln xi plus xi ln activity of ln gamma I. And I'm just going to again expand this out a little bit. So that's going to be RT sum of xi ln xi plus RT the sum of xi ln gamma I. So this is really just expanding this equation. It took a lot of steps to do it, but hopefully you see how I got there. And now we look at this and we see, wait, this step right here is exactly the same way we defined our delta G ideal. So this is our ideal component. And note that this is also the way we define our delta S of mixing, right? Or for an ideal solution, right? We say that delta S is equal to RTXi ln xi or whatever. So we can say that this basically correlates to the entropy of mixing, because it's all of that ideal component. But then this second aspect here, this is all of the non-ideal. If that's all the ideal, then whatever's left has to be non-ideal. And remember how we just reasoned out that this non-ideal portion has to do with delta H of mixing. So what we can do, if you want to be a bit more mathy about all of this, is you can go through and you can say that delta H of mixing is equal to RT, the sum of xi ln gamma I. So if we want to find, I'm going to switch to a black pen. If we want to find delta H of mixing for C, that would be, oh, my battery's running low. Are there any plugs nearby? I feel like, oh, is there one right behind me? That's so ridiculous. Aha. Okay, so we can say the delta H of mixing for the cadmium is just going to be RT, then XC ln gamma C, which would be 8.314 times 800 times 0.5 ln, I think it was like 1.32, whatever we define, and that should give you the exact same answer. So that's another way of looking at it, is that if you want to take a more equation-based approach, more mathematical approach, both of these solutions give you the same answer, the same idea. It's just whether you're a graphy person or a numbers equation person or whatever, you're feeling like on the day. Does that help clear things up a little bit? Beauty. Okay, I'm seeing some thumbs up. We're gonna move on to part 3 now. I think 3 was like relatively short. Don't quote me on. Yeah, look, it gave us times for how to do these. Okay. Else? Oh, also I completely forgot, but like all these equations I've been talking about, we were given most of them in the formula sheet. We were told we weren't going to get any formulas though. They pulled a little sneaky on us. Pardon? Well, we were begging because we were like, we're coming off of COVID. We literally know no equations. We're used to having open book. And he's like, yeah, that's why I'm going to make a closed book. And then we get to the test and we open it up and there's all those equations and we're like,
He just says he doesn't.
I disagree with that. Because I see it from both ways. I think that a lot of this can come down to like understanding of the concept. I don't think that they should give us everything, right? But at the same time, I don't want to memorize a bunch of different formulas. I want to be given them. So anyways, that's a side tangent. Now we're gonna make some graphs. Remember how I was like, oh my gosh, you could be a graph person or a mathy person? Unfortunately, you have to be a graph person for this question. So let us start. it wants us to make a plot basically showing temperature dependence of the activity coefficient versus mole fraction with non-ideal solution where it's positive deviation and negative deviation. So let's kind of break this down. I'm going to start with positive deviation. So we're doing our activity coefficient. So I know positive deviation, that means that our gamma I is going to be bigger than 1. So that's the first thing that I need to be aware of, is that gamma I is bigger than 1. And I'm going to be like, no, yoink, yoink, yoink. The next thing I'm going to be like, what am I actually plotting here? So our y-axis is going to be gamma I. You know, that's going to increase up. And then our x-axis is going to be mole fraction. So I'm going to call this xb. I'm going to go from 0 to 1. Now, I'm just going to try and get a few values here. I know that gamma, because it's positive deviation, it has to be bigger than 1. So I'm just going to say this value right here is 1. I'm going to draw a little dotted line. And I'm going to keep that in mind, that everything has to be above that. Now we need to talk about what actually is going to happen in this case. So, yeah, so I'm going to say that as basically, we can talk about what's going to happen regardless of temperature. We're going to ignore temperature right now. I'm just going to figure out what is it kind of going to look like. I know that as xb approaches 1, at the as it approaches 1, then xa is going to be dilute. And that means, if you remember, you know, back to the first test content, if xa is dilute, that means it's going to behave as Henry's law. And essentially what, you know, Henry's law is xa is equal to gamma a, AA is equal to gamma a xa. But that means that xb, if Henry's law is happening in A, then in B we're going to be having Raoult's law. xb is high concentration. That means it's going to behave like Raoult's law. So basically that means that AB is going to be approximately equal to xb. So gamma B is going to be equal to 1. Do you have to write all this? No, but this is like kind of where my brain is going, so I'm trying to figure out what the heckin' is going on here. So basically, we know that as xb is in high amounts, then we're going to be close to 1 for gamma B. So I'm going to draw that down here. This is going to be gamma B. I know it's going to be close to 1, but it's not going to be at 1 this entire time, right? We just said that it's going to be bigger than 1. So it's actually going to look some, you know, kind of like this. And the reason it's going to have that shape is now we can go back and we can math it out a little bit. We know that we have a non-ideal solution. We have a regular solution. We have the formula ln gamma, I'm going to use ln gamma B is equal to alpha times xa squared. So basically what this shows is that we're going to have some sort of quadratical relationship going on here. Or I guess not quadratic, it's going to be exponential, because now we can say gamma B is going to be the exponent of xa squared. So it's going to depend on xb, but it's going to have like this kind of like exponential shape to it. Yeah, those are my words. And we know that in this case it's going to be bigger than 1. We can have, you know, if you want to be fancy, we can also do the exact same thing for A. It's going to be the opposite of what we have for B. It's going to be like, oh, something like that. But now we want to talk about, so we have like the first part of the question, but it's also asking us for some sort of temperature dependence. And we're like, okay, so how does this actually relate to temperature whatsoever? Wow. So what we can say is we're going to go back. I'm going to get rid of that. We're just going to look at ln gamma is equal to alpha times x. But remember, alpha is defined as our omega over RT, where omega is a constant value. So you can say that ln gamma B is equal to omega over RT xa squared. So what we can say is that ln gamma B is proportional to 1 over T. Just like ignoring everything else. We don't really care. We're just looking at how temperature relates to our gamma. So essentially what this shows is as T increases, our gamma is going to decrease. So the way I drew that on my graph is I did little dots, and I was like, so that's a high temperature. And then at a low temperature, I'm going to do little dots like this. And I was like, So whatever way you want to draw this, just make sure that there's a way to tell it apart. I don't really know how they were planning to deal with that, but this is how I drew it, as little dots. Note that even though it's going to be decreased, right? We just said that as temperature increases, our gamma is going to decrease. Oh, I have this. We still don't go below 1 because it's positive deviation. We're still going to end up around 1 back at, when we're close to ideal at high concentrations, but it's never going to go below that value because we're told it's positive deviation. We're going to do basically the opposite for negative deviation, except in this case, we know that gamma has to be smaller than 1. So I'm going to draw this graph, like xb 0, 1. I'm going to say this is 0, and this value right here is 1. This is going to be 1, and this value down here is going to be 0. Now, in this case, when we're drawing gamma being bigger than 1, we don't really know what the maximum value is, right? There's no theoretical like, oh, gamma is never going to be bigger than 4, We don't have anything like that. So I left the y-axis basically barren because I don't really know what's going to happen there. When we're talking about negative deviation, then we got to remember the definition of ln gamma b is equal to alpha times xa squared. We're taking the ln of this value. We can't take a ln, like the ln of 0 is equal to undefined, right? Like I'm not tripping, it's equal to, yeah, undefined. It's a math error. So we know that no matter what happens with this value, it can't get below 0. So from there, we can apply the exact same logic. We can say gamma b is that as we have really high concentrations of B, really high molar fractions, it's going to be close to ideal. So we're going to be right around 1. But then as we get smaller and smaller away, it's going to get closer, like it's going to deviate from that ideality. It's going to go like, and if we have that's going to be at a low temperature, and then YB at a high temperature, again, we said that it's going to be a little smaller, so it's going to be something like this. And I'm not going to bother doing A unless y'all want to see that. So that's kind of the reasoning there. You can just draw the graphs. You don't need to add all that writing on the side. But for me, when I see something like this and it's like, ooh, draw this situation out, I like to have some sort of mathematical basis behind what I'm drawing because that makes me feel a lot more comfortable with the way that I'm answering. But you don't need that for any means. You could have just, done the practice test and remembered what the answers were and just drawn it on the page. Like, realistically, that's, I think, what I did when I drew this. I just added the math to make myself feel better. And that is the test. So that was a lot of me talking. Are there any questions? Go for it. Yeah, I didn't make that very obvious. Yes. Basically, the question, if we go back to the actual question, asks us to talk about the temperature dependence. So what I did is I mean, I could use multiple colors. I don't know why I didn't. Is I was using a dotted line to represent the same thing, like it's still gamma B, but it's at a different temperature. So in this case, we decided that as temperature increases, our gamma is going to decrease. So what I did is I just decreased it and I did a dotted line. So I'm just going to do a different color to make it a bit more sense. I'm going to use gamma B at a high temperature, and it's going to be a lower value, something like that. The activity coefficient is going to decrease. They're inversely proportional. Well, the ln of that comes down to this relationship here. This is true for all cases, no matter whether it's negative or positive deviation. I'm gonna stop sharing my screen real quick. Kura, do you have any questions? How do we stop recording? Any questions